Hello everyone. Let's continue our discussion on the spice simulations that we did in the last video. So in the last video we did spice simulations for two different devices. One was 1.2 micron device and one was 0.25 micron device, and we briefly explained the observations that we had from these two curves. So let's try to deep dive into those observations. The first observation is this one. So what you see over here, if you see the gate voltage, the drain current, let's say the drain voltage at this point of time is 2.5 volts. Okay, so the drain current at each and every gate voltage at this point at VDS equal to 2.5 volts, there is a quadratic dependence over here. So for example, if you see at this point of time where gate voltage is 0, your drain current is 0. Where your gate voltage is 0.5, you have a small drain current of about let's say 10 microamps. Where your gate voltage is 1 volts, you have some small value of drain current of let's say 40 microamps. And similarly, so it's not linearly increasing with gate voltages, but there is a quadratic dependence on the gate voltage. Okay, and this is what we had proved in our models. While deriving the models, we had proved that from this equation. So this equation basically says that your drain current is a quadratic function of VGS, because it has got a dependency of VGS minus VT the whole square. So ID has got a quadratic dependence on VGS, and that's pretty much proven from this particular curve, or only from the last section of the curve. What we can do, we can take the higher value of VDS, which is 2.5 volts, and at 2.5 volts we can plot the we can plot the drain current at different values of VDS, at different values of VGS, and we'll do that in some time from now. So for different values of VGS at one value of VDS, which is 2.5 volts, you will see the drain current has got a quadratic dependence. Your drain current quadratically increases with increase in the gate voltage, and that's what we have proved in this particular equation. That's the first observation. But on the other hand, if you see for a short channel device, initially when you look into the lower values of gate voltage, you still have a quadratic dependence in this area. For example, at 0 volts you have zero gate current. Okay, you have zero drain current. At gate voltage of let's say of 0.5 volts, you have some amount of drain current, let's say 10 microamps. at at a gate voltage of 1 volts, you have got a drain current of let's say 40 microamps, and so on. So in this area things are still quadratic, but as you move from this point till this point, things are linear. Your drain current, your current at this point and at this point and every point after that, it is linearly increasing with your gate voltage. Okay, so that is what's it's something different we are seeing from the short channel, different that we are seeing from the long channel device. So 1.2 micron is a long channel device, and anything below 0.25 micron is referred to as short channel device. And this is one of the short channel effect, or this is one of the effects that you see when you go into lower nodes. Okay, and the reason why is this happening, the reason is the velocity saturation. I'll come to the concept of velocity saturation in some time, but before that, to make things a bit clear in a graphical way, what we'll do a bit of spice simulations. We'll do some small simulation where we keep the drain voltage constant to be 2.5 volts. Same thing over here, and we will vary the gate voltage. In the previous case, we had drawn ID versus VDS at different values of VGS. We'll do the same thing. We'll plot ID versus VGS at different values of VDS. Currently, we'll take one value of VDS, which is 2.5 volts, to make things a bit simple. Okay, we'll take one value of VDS 2.5. We'll keep the gate voltage, we'll keep the drain to source voltage constant. Okay, and vary the gate voltage and measure the drain current. That's what we are going to do. Same thing, we'll do it for 1.2 micron device, and we'll do the same thing for 0.25 micron device. Okay, and there will be a very small change in this spice deck that will help us, that will enable us to get through this one. Okay, so let's do that. Let's try to focus on the drain current versus the gate to source voltage at constant value of VDS. Okay, so I have a spice deck already ready over here. So the only change, the spice deck remains exactly the same. The only change will be at this line. Okay, so this line specifies that now you vary your gate voltage from 0 to 2.5 at steps of 0.1 volts at every value of VDS. So now VDS or VDD is being swept from 0 to 2.5 and the step size that we have given is 2.5 because we want to look into only one value of VDS, but we can always sweep it from 0 to 2.5 at steps. But in this case, just for the sake of simplicity, we'll be looking at one VDS voltage, which is 2.5, and will sweep your drain to source voltage or VDD from 0 to 2.5 at a single step 2.5. Okay, and at every voltage, at every step of VDD, the gate voltage will be swept. That's basically the syntax. I forgot to mention it in the last video. The syntax basically says that whatever is there in the left hand side, that will be swept or tuned at every value of what you see in the right hand side. Okay, so let's bring up the spice simulator over here. This is the folder where we have kept everything. Let's minimize this one. Okay, and this is the spice simulator. So we'll first go to this area. CD will enter this area. Okay, and we'll copy paste the name for this one. We'll source the circuit. So I've just given a name. It's called IDVG. It is different from the one which we gave. It is IDVD in the previous case, just to differentiate this file from the IDVDS file. Okay, so this is the circuit. This is the spice simulation we are doing for drain current versus gate voltage at one constant voltage of VDS. Okay, so that's pretty clear. So we will source the circuit, and now we will see what all plots are available. Before that, we'll simulate it. So the command to simulate is run. Okay, and we will now look into the plots which are available to us. So again, we have the node voltages and current at VDS, which is VDD branch, and the gate current. So this is the current that we are interested in, VDD hash branch. Okay, so we'll set the plot, and the plot name is, again, we are looking into the DC transfer characteristics. So let's put DC1. Okay, display, let's come back to the plots we have. So we are interested in VDD hash branch. So we will plot negative VDD hash branch, and yes, there you go. So you have now this particular plot for the gate. This is the drain current, and this is your VGS, gate voltage, at one constant voltage of VDS. So VDS is held constant. So basically, if you see, there are two plots. One is this yellow line, which is at VDS equal to 0. There will be 0 current because VDS is at 0, and there will be one more plot which is at VDS equal to 2.5 volts. Okay, so if you see this one, this looks fairly quadratic, and this is not very obvious from this plot unless we compare this plot with the other one, with the short channel one. So let's minimize this one. Okay, we'll minimize this one, and we'll take the other one. So this was for 1.2 micron, and this one will 0.25 micron, sorry. So everything remains same. We are sweeping your gate voltage and drain voltage. Only difference is the channel length over here. Okay, so we will source this one as well. We can do it in the same simulator. So let's close this. We'll copy source.cir. Okay, now when you display, or first we'll simulate it using the command run. Okay, now we will do a display. Okay, we have the same thing, but before that we have to set the plot. So we'll set the plot. So DC1 was the one for the previous DC transfer characteristics. For the new one, we have DC2. So let's set this particular plot. DC2 is the plot for the latest one. So we have DC2. Let's display the plots and now plot them. VDD hash branch. Yeah, and this is the one. So what we have to do is we have to take this curve and we have to take the other one. So we have to do this comparison. We have to take these two particular curves and do the comparison. So if you see over here, the sweep is pretty much quadratic, and over here, if you see, this area is pretty much linear compared to this one. This is too curved, and this is a linear one. So, okay, so what we'll do, we need to explain this thing in even more detail. So in the next video, we'll plot them side by side. We'll take the ID VGS curve for the long channel, and we'll take the ID VGS curve for the short channel, compare it side by side, and see what do we get. And we now, since we now have the spice simulations for the drain current, for the drain current versus gate voltage, we have this result, so we can take these results directly and do analysis based on these graphs. So let's try to analyze this curves in the next video. Thank you.